Hi everyone, hope you guys are doing really good. Today we are going to start a new discussion that is on path planning of robotic manipulators. Remember, in the very initial phase of this course, we introduced one application. That was to start from point A and go all the way to point B following a surface. And this surface was needed to be cleaned using a grinding wheel. And you were required to use a robotic manipulator that was able to do that. So what we did introduced at that particular stage was that we have to start from this point, but once done, we have to move to adjacent point, and then to the next point, and then to the next point, and so on and so forth, eventually reaching to the final point B. But this whole activity requires a bit of planning, and this path is needed to be defined. And that is the question that we are trying to resolve in this particular discussion. So let's start the discussion now. I'm going to start from a different application today, that is of pick and insert application using robotic manipulators. This is just like a starting example, only to identify what it takes to plan a path. What is the motivation behind it? What are the necessary ingredients for the path planning exercise? And we are going to set up the discussion for the subsequent in detail, in-depth analysis. So let's see how it goes. Now in this particular scenario, what you can observe is that you have this part which is needed to be picked up. And this pickup location can be identified as location A, and it is going to have certain set of coordinates like X, Y, and Z of point A. And obviously you can observe that this is the location where this part is needed to be inserted. And if this location is location B, you can identify that you are going to have certain set of coordinates for that as well. Now, if a robot has to perform this whole activity, it has to start from somewhere. Generally, in the very initial phase, it will start from a home location, somewhere away from this whole set of points. So this is also going to have certain set of coordinates for the home location. So the robot has to start from home location. It has to access this part at point A, and then it has to follow a certain path all the way to point B as well. And this is the whole activity which is needed to be planned. So the very first phase is how you're going to start from home location and reach all the way to point A. And that is the first phase of motion planning. Now in this segment, starting from home location all the way to point A, the robot must ensure that this segment is collision free. This segment as well as all the other segments of the motion. So I'm going to write that one down over here. So this path is going to be needed to be collision free, and it must be done in a fast fashion so that the time consumption in performing this whole activity is brought to some optimized level. Now, assume that your robot has started this whole activity starting from home location to accessing point A, and it is in the middle of this movement. Now, at this particular instance, you can see that the tool center point is placed over here. Now, if the robot has to access to the next point, just like adjacent to it, that must be given like a reference signal to it, like a guidance given to the robot that this is going to be the next point that it needs to access. Now, this is needed to be given to the robot, and this path planning exercise requires this information to be computed. At the next instance in this whole activity, you can observe that now the robot is very close to picking this object up. Now, but there is an obvious problem as well. If the robot needs to pick up this part from this location, the gripper is needed to be further opened up, or you have to do some sort of reorientation of the wrist or the gripper. So for that reason, I would write these questions over here or observations over here. Orientation may be an issue. And also gripper is needed to be opened up or further opened up. And in other words, if I may say that, I will be very extra cautious or careful in this location. So this is something like I need to have a careful operation performed over here. Now, assuming that your robot was able to successfully grab the component up, the component is needed to be shifted to the other location, at location B. And in order to follow that particular route, the robot must have a specific path followed. So that path may have this kind of shape incorporated. Now, this particular profile is needed to be given to the robot so that the robot is able to follow it. And this is also part of the path planning exercise. But what if in the middle of this path you have some sort of a big obstacle? Let it be an obstacle over here. So in that particular scenario, the robot must have the ability to change the route or alter the path followed. So potentially you may have a D route over here, something like this, and then access this whole point B from this orientation. And that's why obstacle avoidance is needed to be carried out all the times. And I should also write down that this is an obstacle so that it is well indicated. Now, when the robot has to perform this whole activity while avoiding the obstacles, it has to be careful about consuming not that much time. So that is going to be another important consideration to be added. So time optimization or energy optimization, if I may say that. But I'm going to assume that this path has been carefully planned in this whole path planning exercise, and the robot is able to avoid the obstacle, consume lesser time and energy in reaching to the point location B. So I'm going to move on. Now at this particular location, you can see that the robot is now ready to place this component in the hole that has been provided at location B. But once again, there is this fear that this pin may not be appropriately inserted into the hole. And that's why this section is needed to be also the section where careful activity is needed to be performed. So you need to be extra cautious and careful about this segment as well. Probably performing this activity in a fast fashion may not be required or may not be appropriate. So you need to be slow and you need to be careful and you need to be getting this feedback from some sort of sensory sensor or feedback placed at the robot wrist. And that's why this activity is needed to be carefully planned. And also this path is now needed to be handled in a fashion that you follow a straight line as well. So this path is needed to be extra carefully planned. And oftentimes when the robot is needed to perform the insertion operation, some additional requirements may be added. For example, the wrist compliance. And that may also place some additional requirements on the path planning exercise. In a nutshell, you can readily identify that this whole activity is needed to be planned in a methodical fashion. You have to ask your robot to start from a home location and reach to the proximity of point location A. But this path is needed to be collision-free, and this activity is needed to be executed fast enough. In the middle of this activity, you have to find out each and every point like a reference signal. This reference signal, by the way, the controller will resolve it into the joint space reference signals, but that is another story. But once in the proximity of point location A, the robot has to perform this activity in a very careful fashion so that the orientation of the wrist and the gripper arrangement, whether it is opened or closed, is properly taken care of. Once the robot has grabbed this component up, it is needed to be shifted to the other location, but that activity is also needed to be carefully planned. And in that, you have to ensure that the obstacle-free assurance is there, and time and energy consumed in this whole activity is also accounted for. But once it is closer to the point location B, once again, you need to be careful. And that careful operation is necessarily needed because this is an assembly operation, which will further require certain compliance and certain other arrangements to be ensured. So you can see now that this whole activity in the application that we have chosen for this whole discussion is, when decomposed into smaller segments, it contains quite a lot of information which is needed to be well understood. And now you know that a seemingly very simple, straightforward task of picking an object up from a certain location and placing it into a box or into a hole is needed to be carefully planned. And that is not something which is very easily or automatically done. So you have to plan this activity, and that's why it is an important issue to be handled. So this is what we're going to do in the remainder of this discussion. Now we can define motion planning. It is the process of breaking down the whole activity into discrete set of motions, which are going to satisfy all the motion constraints. And in that process, possibly we would like to optimize some aspect of the movement, for example, time, energy, etc. Let's go through a few other examples, and this will make you understand that path planning exercise is not limited to the one application that we have discussed so far. The spectrum is very wide. I'm sure that most of you guys must have played with such puzzles. The task was to untangle the two bars from each other. This puzzle and many other such puzzles have been developed by researchers as benchmark problems to assess the capability of planning algorithms to find solutions. In the non-industrial settings, probably room cleaning robots are the most popular robots. And these robots are used to clean the floors autonomously. On your left, you can see one robot doing this whole activity in a reactive fashion. It is wandering and cleaning the space up, but probably not in an efficient manner. But the robot on your right, you can see that it is performing this whole activity in a very methodical fashion, covering the whole space up and doing this whole activity in an efficient manner. So motion planning algorithms can be used to allow your robots to perform such activities in an efficient manner. Now this is another example where motion planning algorithms can help us out. We have a wiper assembly inserted inside a cavity, and it is needed to be taken out from the system. Now, in order to do that, you have a constraint that the opening of this cavity is somewhat very small, and you have to reorient this whole assembly in a specific way so that it can easily be taken out from the system. And for that, the KinoCam uses motion planning algorithm to allow reorientation, repositioning, and the path to be executed in an efficient manner so that this activity can be performed. Automobile industry uses these robotic manipulators very frequently, and these manipulators require motion planning algorithms to help them out. Now, in this example, where Volvo Cars scenario is simulated, you can see that multiple robots are doing their job on one car. Now, in this case, all the robots are going to access their workspace or their task from different points. So they have to get into these spaces, difficult spaces, perform their job, spot welding, inspection, and other jobs in a very efficient manner or a planned fashion. Now, for that, planning algorithms would be required. In addition to that, on one car, there are multiple robots doing their job. Now, all the jobs are needed to be completed in a very specific time so that next car can be served. So for that, you have to use all these planning algorithms for multiple robots to start doing their job at a particular time and stop their work or complete their work in a stipulated time as well. So for that reason, motion planning activity would be required in such applications. One very interesting problem that is frequently used as a benchmark problem in literature is called piano movers problem. And in that, you can see on the top view that there is this apartment, and inside that apartment you have furniture, chair, table, sofa, and stuff like that. And you're required to move this piano inside this apartment from one location to the other location. And in this particular application, you can see that there are 3 robots doing this activity. So a motion planning algorithm in this scenario would be required to ask these robots to coordinate with each other. In addition to avoiding uh, collisions, in addition to executing this whole activity in an appropriate fashion, starting from a starting location and reaching to the final location. So for that reason, a good planning algorithm would require quite a lot of additional exercises to be executed so that this coordinated action can be done in an efficient manner. Path planning activity may be required for humanoids as well. In this application, for example, you can see in the top row, this robot in a simulated environment is needed to grab something under the table. Now it has to perform this activity in a very careful fashion because the table is hindering the field of view. So it has to coordinate all the joints, knees, ankles, hips, in order to reorient itself so that it can see and observe where the object is placed and access it. Once it needs to access it, it has to move the upper limbs, the arms, in an appropriate fashion so that it can grab it. And then for the retrieving exercise, it has to once again stand up and place the object over the table as well. So seemingly a very simple, straightforward task that we can very easily as humans do. For humanoids, it would be a very difficult task. And planning algorithms would help these robots to perform these activities in a better way. Now consider that your robot is a mobile robot and it is moving inside a building. So it is an indoor scenario. Now, if it is moving indoors, oftentimes what happens is that the environment is needed to be mapped. And for that, there is one approach which is used called simultaneous localization and mapping, also called SLAM. So it would mean that not only the robot is mapping, it is also in a simultaneous fashion localizing itself as well, vis-a-vis the other arrangement or the floor plan of the building. So in this particular example, you can see that the robot is traversing inside corridors and observing different sections and rooms and building a map of the environment while in a simultaneous arrangement localizing itself as well. So in that sense as well, you need to ask your planning algorithm to help this robot up in order to move inside these corridors, avoid cyclic behaviors, avoid getting into the traps or local minima situations and stuff like that. So for that reason, motion planning activity is needed to be carefully planned. Here in part A, you have another interesting application. You can see that the robot is going to start from here. Now, interestingly, what has happened in this case is that you have placed a few constraints on the motion. In this case, the interesting constraint is that the robot is only allowed to take the left turn. So it cannot and it will not move to the right. And if it is the constraint put forth, then it has to find a way starting from this location all the way to the final location over here. And it has to traverse the whole difficult scenario. Scenario is difficult in a sense that you have uh, uh, confined spaces, you have obstacles which are sparsed apart, and then you have to get inside this chamber, this narrow alley, and then you have to avoid all these obstacles, eventually reaching to the final location. And it has to perform this activity while taking only left turns. So you can see a few iterations in blue and in red. And once all the permutations and possibilities have been exhausted, it will try to find out the best possible solution, starting from this location, going all the way to the final location. And that is shown in yellow. So the effectiveness of a path planning exercise when you put additional constraints would be tested in this scenario. And that is an active area of research. And it is not without any practical applications. For example, over here, you can see the parts of Airbus were required to be traveled across different manufacturing stations. And for that, the route was needed to be carefully planned. So motion planning algorithms were used to perform this whole logistics, complex logistics activity efficiently performed. Here you can see two examples. In example A, you can see reckless driving. You can see that the car is starting from here and it is trying to reach to the final location over there. And it is avoiding all these crossings and roads. So obviously it is reckless and it is not advisable. But in this particular case, the motion planning algorithm is going to help this car out to quickly reach to the final location. In example B, for example, you can see red team participating in DARPA Grand Challenge, and in that it was required to traverse at high speeds over rugged terrains and over long distances. So motion planning algorithms were necessarily required to be incorporated. This is another example, a more recent example. In this case, the autonomous driving, which is much developed now, is being executed, and you can see that the car is trying to find multiple ways and assess multiple ways to quickly jump from one place to the other, move from one place to the other, and it has to assess all the different possibilities that are presented to it. Uh, in terms of planning as well as reactively addressing the scenarios. So this is going to require motion planning of some sort to be implemented as well. Now in this continuation, the overall motivation is that for the end effector, we have to choose a path which is going to avoid collisions and also the singular configurations. For singularities, we understand the configuration of the robot is going to be helpful. But the problem with collisions is that these obstacles are defined in the workspace. So we have to figure out the difference between the workspace and the configuration space. And if there is an obstacle in the workspace, and in order to avoid colliding with it, we have to map this thing onto the configuration space. So that is going to be one major motivation to perform this motion planning exercise. For singularities, obviously, these are defined easily in the configuration space. So we have seen this thing already. Now, this complexity of avoiding obstacles which are going to be mapped onto the configuration space is going to grow even bigger when you have multiple degrees of freedom in your manipulator. For two-link manipulator, for example, this would be a bit easier job, but for n-link manipulator, it is going to be a bit complex job. So we have to find ways to do that, efficient ways to do that, and that is one of the motivations. And for that reason, we have to find out those methods and approaches which are going to avoid explicit descriptions of the obstacles. And for that, in this particular course, we are going to use potential fields and some sort of gradient descent algorithms. And in the last phase, we are going to use probabilistic roadmaps. I should emphasize that at this particular stage, because we are not going to get into the deeper discussions on the path planning, these are just like the starting approaches or methods. But the serious readers and interested researchers are going to dig deep and see some other better methods to achieve that. But this is just like the starting exercise. We will try to accomplish as much as we can in the limited time available. Now, it is important to identify the basic ingredients of planning. So the very first ingredient that we have to look into is state. Now, remember, in all these applications, we have uttered these words over here: starting location, final target, or final location. So these are the two states: initial state and the final state, obviously, but in between you have intermediate states, multiple of those intermediate states. So you have to define all these states in an appropriate fashion. So there must be in your planning algorithm ability to define states. Now, in addition to that, time is also important. Although we have not uh, said the word like trajectory in this whole discussion so far, but we are going to make use of trajectory planning later on, and that would require the time information to be added in the whole problem. It is also important to identify, when you are going to move from one state to the other, what are going to be the actions performed. So actually, this is going to be a state action pair that we are going to be interested in. And that's why the planning algorithms would require these pairs to be, in certain cases, in often cases, explicitly defined. Moving on. Now, in order to allow your end effector to start from the initial state and end at the final state or reach the final state, while performing all these actions, there must be some sort of plan to execute that activity. A plan that may require a priori information provided to it of all the obstacles, of all the workspace that is there, and it may have the ability to reactively perform uh, to react when there is some sort of unstructured information given to it or scenario given to it. For example, a moving obstacle, when it is presented to the robot, how the robot behaves is going to be a very tricky aspect of this whole planning exercise. Now, in addition to that, you need to perform or define a criteria which is going to ask uh, the planning algorithm to assess the ability of this planning, or assess the effectiveness of the plan. And for example, one can be like, is the plan feasible? Or the other one can be like, is it optimal? If whether it is consuming more resources or less resources in terms of time as well as energy and all that. So feasibility and optimality are the most commonly used criterias for motion planning exercise. So that is going to be one of the major ingredients in this whole activity. And then you can place certain additional constraints on the system. So those are going to grow uh, uh, task to task, or application to application, and that is going to add one more set of complexity or layer of complexity in the planning exercise. And obviously then you have all these planning algorithms, just like the ones that we have shown in the previous slide, which were like potential field methods, and in that active potential field methods and uh, uh, virtual potential field methods and local target methods and radius curvature methods and stuff like that. So there are so many of those, and all those algorithms associated with them and with all the pros and cons of specific planning algorithms are going to be also important there as well. So I think I've been talking too much. So this would be appropriate now to take a break. So this would be end of part one. In part two, we are going to cover some more basics of the planning exercise. So wait for that.